Alright, so what we're going to look at in this video is the idea of percent error. Percent error is a representation of how close our values are, our measured values or our calculated values are going to be to what is considered to be the accepted value or the true value. Another term for these two things is how close our experimental values, the things that we're figuring out, are close to the theoretical values, the values that have been found by other scientists and other experiments before us. So to figure out percent error, you're always going to look at an equation. That equation is essentially a giant division problem. So what percent error is going to be is you're going to take your theoretical value, we're just going to abbreviate that THEO. We'll subtract from the theoretical value the experimental value, we'll abbreviate that EXP. Divide that difference by the theoretical value. So we've got theoretical minus experimental divided by theoretical. Depending on how the values of our numbers here, you could end up with a negative percent the way it is written right now. That's not something we want. So percents aren't usually representative as a negative percent. So what we do is we have these absolute value signs in here. So even if this ends up being a negative number, we're more concerned with the absolute value of that, not the actual negative number. And then once you take the difference of your theoretical and your experimental and divide it by theoretical, you turn it into a percent by multiplying by 100. Right, so this is your equation here for percent error. Percent error equals theoretical minus experimental divided by theoretical times 100. Pretty simple. So let's look at an example. Let's go back to our densities examples from before. Let's say we have a box again that we're going to figure out the density of. So we're going to measure the mass, measure the volume, use that equation for density. Density is mass over volume. And let's say we do all that out and we find out that the density of this box that I have here is 2.9 grams per centimeter cubed. Right? So the density that we find of our box is 2.9 grams per centimeter cubed. And we also know that our box is made out of aluminum. So this value here, this 2.9, is the value that we have determined for what the density of our box is, 2.9 grams per centimeter cubed. That makes this our experimental value. Your experimental value is always the one that you have determined through your experiment. The thing that's going to come up here though, and if you remember, if you've seen some of the other videos, you might have already noticed this, the density of aluminum has been found time and time again to not be 2.9 grams per centimeter cubed. The density of aluminum is very much accepted, solid aluminum metal, to be 2.7 grams per centimeter cubed. So what that means here is that our accepted value and our theoretical value, our experimental value, our 2.9, and our theoretical value, our 2.7, are different. So we can use a percent error to put into numbers exactly how different they are. So to do that, we're going to follow our percent error equation. So percent error is going to equal our theoretical. The theoretical, again, was the value that is accepted in sources and in society, which is the 2.7. That's your theoretical. Just label that so we don't forget. So we're going to go 2.7 theoretical value minus experimental. That's the value we figured out in this experiment, which was 2.9, divided by our theoretical, the 2.7 again. And then we have to take this whole thing and multiply it by 100 to make it into a percent. So if you go through and do that, what you'll come up with is the percent error. You will find the percent error. And again, that's a numeric representation of how close your values are to the true value. So 2.7 minus 2.9 is 0.2. Oh, remember that would be negative 0.2, but we have our absolute value signs in here to make this all right. So negative 0.2 absolute value, that means we're talking about the number 0.2. We can kind of drop the negative. And then we would divide that by 2.7 and multiply by 100. This would give us a percent error equal to 7.4% for our density analysis of this cube. So what that means, our density should have been 2.7. It was 2.9. Numerically, that is a difference of 7.4%. So our experimental value is essentially 7.4% off of our theoretical.